In this lesson, we're going to explore polynomial functions that have complex roots. Let's review the fundamental theorem of algebra, which states that a polynomial function of nth degree has n zeros, and they can be real and complex combined. So how do we find zeros of a function? Well, we let the y value be 0. And you can use various methods. So in this one, we would add 1 to both sides, and we'd get 1 equals x squared. We'd square root both sides, and the moment we take the square root in an equation, we need to remember that there are 2 possible roots. So this has positive and negative 1. In the second one, well, we can again let y be 0. This time, I'm thinking I can probably factor this into, let's see, x minus 1 and x minus 1. So by the ZPP, I get x equals 1 or x equals 1. And in this third one, if I let 0 be y, then I'm going to solve by subtracting 1 from each side, which gives me x squared equals negative 1. Take the square root of both sides, and I get x equals, well, plus or minus I. So this time I have, this would be a pure imaginary number, but notice that there are again 2 solutions. So interestingly, this leads us to something known as the conjugate root theorem. And this is probably rather intuitive. So suppose f of x is a polynomial function. If a plus bi is a 0, well, then we've kind of noticed that its conjugate, a minus bi, is also a 0. So what we're stating is they come in pairs. So let's illustrate how we can use this. So if 3i is a 0 of this given quadratic, show that its complex conjugate is also. Well, if it's a 0, that means that when I do synthetic division, I will get a remainder of 0. So I'm going to set up my synthetic. Notice that I need 0 as a placeholder. I begin by bringing down 1. And now I've got to do multiplying with an imaginary, but this one's not too bad. So 0 plus 3i now is 3i. And 3i times 3i is 9i squared. Well, just remember that I squared is equal to negative 1, so it's actually negative 9 right here. I add, and I get 0. Now I'm supposed to state that its conjugate is also. So if the conjugate is also, that means that negative 3i must be a 0. So I'm going to just do synthetic with the remaining depressed polynomial. I'm going to bring down 1. I'm going to multiply. And I'm going to add, and I can see that it is indeed both 3i and negative 3i are zeros. If 5 minus 2i is a 0 of f of x, show that its complex conjugate is also. So I'm going to show that 5 plus 2i is indeed a 0 of this given function. So my coefficients would be 1, negative 10, and 29. So I'm going to begin by bringing down 1, then I'm going to multiply, which would be 5 plus 2i, add, combine your like terms, which would be negative 10 and 5, so negative 5 plus 2i, and now I need to multiply, and I'm going to do that off on the side, so you can see the distributing. You may get better and not need to do this, but this would be negative 25. Plus 10i, and then distribute this one, so it would be minus 10i plus 4i squared. Notice that my 2 middle terms drop out, and 4i squared would be 4 times negative 1, so I'd end up with negative 25 minus 4, or negative 29. Then I add, and I get a remainder of 0. So I see that its complex conjugate is also a 0. In the next problem, I'm given a cubic function, and I'm told to find all the zeros. Well, I know that, again, negative 5, it's given, is a 0. So I'm going to begin by, again, doing synthetic division. By the factor theorem, I know that if something is a factor, the remainder will be 0. So I bring down 1, I multiply, that's negative 5i. And here I get a complex number, and I always put my real part first, so it would be 2 minus 5i. It's a binomial, or complex number. Now I'm going to multiply that by negative 5i. So I am essentially distributing. Negative 5i times 2 would be negative 10i. I kind of write that second. And negative 5i times negative 5i, well, that would be positive 25i squared. 25i squared would be the same as negative 25. Now I add vertically. That would be negative 10i, because 25 and negative 25 would cancel. Now I multiply negative 5i times negative 10i. That would be positive 50i squared, which is negative 50. I get 0. So this remaining depressed polynomial here is ugly because it has these complex coefficients on the x and the x squared term. But by the complex conjugate theorem, I know that if 5i is a 0, negative 5i is also, or other way around here. They come in pairs is the big idea. So I'm going to redo my synthetic, but this time I'm going to use positive 5i. So I bring down the 1, and I multiply, gives me 5i, and this time it's going to be much easier. My coefficients in this depressed polynomial had imaginary and complex. When I do it again, if I've not made any mistakes, it's going to switch back to all real coefficients. So 5i times 2 will be positive 10i, and sweet, there it is. So this is showing me that my remaining polynomial, the depressed polynomial there, is x plus 2. So if I were to write out this entire function, f of x is equal to x plus 5i. From this 0, the corresponding factor would be adding. The next 0, positive 5i, would have x minus 5i, and this remaining depressed polynomial would be x plus 2. So there it is in factored form, and then my zeros are x equals negative 5i, positive 5i, negative 2. I'm going to do one more here. We're starting with a quartic function, and we're told that 1 plus I is 0. Well, because they come in pairs, then I also know that 1 minus I would be a 0. So I know I'm going to be doing synthetic division probably several times here. So I'm going to pick off my coefficients. We don't need any zeros as placeholders. And here we go. We're going to bring down, and now we're going to multiply, add. This would be negative 3 plus I, again putting it in the correct form. Now I'm going to multiply 1 plus I times negative 3 plus I. Until you get good at it, you may need to write your steps over on the side. So I distribute the 1 would be negative 3 plus I. Distribute the I then would be minus 3I plus I squared. Combine my like terms, this here would be negative 1, so I'd have negative 4 minus 2I. I add would give me positive 4 minus 2I. Okay, so I'm back to multiplying. This would be 1 plus I times 4 minus 2I. So I end up distributing again, would give me 4 minus 2I plus 4I minus 2I squared, which would produce 6 plus 2I. When I add, that would be negative 2 plus 2I. And one more set of multiplication over here would be 1 plus I times negative 2 plus 2I. Distribute the 1 would be negative 2 plus 2I minus 2I plus 2I squared. So combine your like terms, and middle terms here would cancel, and I get negative 2 minus 2 would be negative 4. Add, and I get 0. So kind of ugly, this depressed polynomial. And the good thing is when I go to do synthetic this second time, it's not going to be nearly as ugly. So I know that my complex conjugate of 1 minus I is a factor. So I'm going to multiply. That's going to give me 1 minus I. I'm going to add negative 2. The i's would cancel. All right, so now I distribute. That's going to be negative 2 plus 2i, which would produce positive 2. And multiply again. 2 times 1 minus I would be 2 minus 2i. Add, and I get 0, which is so much simpler than what we had to go through before. All right, so now what do I have here? Well, from this point, this is my constant, this is my x to the first, and this is my x to the second term. So presently, I have a polynomial with two factors. One would be x minus, the first one would have been 1 plus I. I'm just going to do a double set of parentheses here to help your eyes see it. X minus 1 minus I. And then what's left here would be 1x squared minus 2x plus 2. I'm just going to clean up this first one to make it be x minus 1. Fix that 1 minus I, and this one here would be x minus 1 plus I. And I'm looking at my third trinomial, and I don't have any factors of 2 that are going to add to negative 2. Why do I care? Because I got to find my zeros yet. So here it is in factored form. It's not going to break down any further, but to get all of my zeros, I do believe I'm going to need to do the quadratic formula over here on this one. So this is x equals, negative b would be, zoom out here, 2 plus or minus the square root. B squared would be negative 2 squared minus 4 times 1 times 2 times a times c all over 2 times 1. So my discriminant, which is my radicand, would be 4 minus 8, which is negative 4 all over 2. So it looks like I'm about to get 2 more complex zeros here because I have the square root of negative 4. So that would be 2 plus or minus 2i over 2, which is the same as 1 plus or minus I. So interestingly, look, I've got the same one. So what does this mean? My zeros are there twice. So my 0 is 1 plus I, and it has multiplicity 2, and 1 minus I also has multiplicity 2. So there are 4 total zeros for this quartic function, which we knew there would be by the fundamental theorem of algebra.